Hello, welcome back to Python 8. Today I'm going to be covering filters and statistics with you. In the last video we covered how to make a graph with multiple lines. In this video I'm going to show you how to clean your data. So let's begin. So here we are in Jupyter Labs. First we're covering the mean, and then standard deviation, and finally a Gaussian filter as well. And then we'll cover error bars at the end also. So we've got some nice graphs now, but we could do some nice data as well. Fortunately, we've got some functions and some handy mathematics, so we're able to manipulate and analyze our data and let it be useful to us. So to begin, we're just going to cover what the mean is. So the mean, you've likely seen this already, it's the sum of all values in a collection, then divided by the number of numbers that you've just summed up. So you've likely seen that before. I'm not going to linger on it too long. We're going to be using the mean in the next video to plot a graph that's known as a rolling average graph. That's when we're going to be using the mean. There's a function for it as well. It's numpy.mean, and you input your array. So it's going to sum up all of the values in your array, and it's going to divide by the length of it. So if I execute this here, the mean apparently of this array is 5. And because it's 5.0, you can probably guess that it's done a float division and not a 4 division. So next up is the standard deviation. You've likely seen this before as well. The standard deviation measures the spread of data values from the mean value. A typical rule from statistics is that approximately 68% of your data points will lie within one standard deviation. I'll show you the numpy function just now, and I'll explain further what the standard deviation actually is as well. So the function is numpy.std for standard, where array is an array-like object, so that can be your list, or it can be an array as well. The function's sort of intelligent, it just handles whatever you give it. So we've got a numerical example here. I've got a collection of heights in centimeters, and I'm calculating the standard deviation and the mean, and I'll show you the mean and the standard deviation. So the mean here looks like it's 176.75 centimeters of these 4 values. And our standard deviation, that is the spread of these values, is about 6.38. So we've got quite a lot of values there. I'm going to round it down with the round function. Now we get 6.38. So the number 6.38 is the value of one standard deviation. So the values we inputted were in centimeters. So one standard deviation includes values 6.38 centimeters on either side of the mean. If you were to add 6.38 centimeters and take it away, then you would get about 68% of your data points if you had a larger pool of data points. And if we got the same standard deviation from that pool as well. So 2 standard deviations would be 2 times the single standard deviation value. So if we do 2 times 6.38, we get 12.76 centimeters. And so this is equal to 2 standard deviations, and this would be 95% of our data points are now covered by 2 standard deviations. So we're going to be using standard deviation to make what's called a fill between graph in the next video. That's a graph that's got a shaded region, so we're going to be displaying one standard deviation on either side of our data line. So finally, a Gaussian filter here. A Gaussian filter smooths over the fluctuations in our graphs. It reduces the amplitude of peaks and troughs, and high frequency noise is very easily filtered out, and it's returned as a smoother line on our graph. So the Gaussian filter is the first function from the SciPy library that we're going to be using. So this is it here, this is how you call it in. It's got 2 parameters. It's got input, which is an array containing the data to be filtered and smoothened. And it's got the sigma value as well. And that's a variable that controls the strength of the smoothing that the filter performs. So in simple terms, sigma controls how big of a window of data that the Gaussian filter takes into account. And so the larger the data, the greater the reduction in amplitude, because you're sort of taking into account the average or the values of all of that data. So if you take a very small sample, there's maybe only a wee bit of filtering. If you take into account a wide range of values, then you're going to smooth out all of that. And it returns to you an array of new values that are now filtered and can be plotted on the y-axis. So it gives you new y-axis values, basically. So here we're importing it in. I'm using a reference name as well. I'm actually bringing in the function from this library. So from the library name, import this function. I'm importing a single function. And importing matplotlib as well, so I can show you. So now it's been imported. We no longer need to call the library name whenever we're using that function. So in this bit here, I am making some random x values and some random y values as well. I'm using the random library, or the random function, to add a bit of noise in. You'll see what I mean. So I've got about four sine waves, and I've introduced some noise to them so we can see what the filter is going to do. So down here, I'm using the Gaussian filter function on y, which is all the y values in here. So these are the noisy ones. And I'm only using a sigma value of 1. So that's pretty weak for now, but it might be enough with this number of data points because we've only got 50 data points in here, only 50. So when I plot this, I'm putting the filtered values into a new variable called filtered, and I'm plotting that with the x values. And I plot that, and look at the difference. So up here, all the noisy data, lots of noise in the peaks and troughs especially. So these tiny spikes have been turned into a smooth line all the way through. So you can better see what our data actually looks like beneath all the noise. So let's try it with a few more data points. I'm going to up this to 500. So you can see there's a lot more noise now. You've maybe seen figures like this in scientific studies where they do a study and there's a lot of noise and they maybe overlay a filtered line on top to show you the general trends. Maybe remember the 7-day rolling average in COVID? They would have the daily number of cases and they would have a rolling average over it to show you generally what the trend was. So you could overlay the filtered line on top of this. So in our filtered line here, there's still a bit of noise. That's telling us that our sigma value isn't strong enough. So let's increase it to say 4. So we put it up to 4. There we go. Much smoother line. There's still a wee bit of noise in here. It's not entirely smooth, but it's done a good job at reducing all of this. If we take it up to 6, I'm pretty sure all of that will disappear. Yep, there we are. Much smoother. Now you have to be careful that you don't smooth the function too much. I'm going to show you way up in the extreme regions here when you go too high on your sigma value. This is what you get. This is terrible. What does it even mean? It doesn't represent your data at all. So when you go too high, when you go overboard on your filtering, it doesn't. You don't get a good representation of your original data. So you need to be in the right range of sigma values. Too weak with 1, too low, you still get noise. Too high, 100, you get nothing at all. So that's Gaussian filter, that's how you use it. You use it to smooth out the noisy data. So maybe we'll use it on the PT1000 especially. That'll be really useful in that. The final thing here are error bars. So this is maybe useful for your laboratory graphs and your lab reports. There's a function for it, it's plt.errorbar. You can put in your x values, your y values, and then the error in these values. So if you have an error in your y value, maybe you've measured it, you've taken into account the systematic uncertainty, the measuring uncertainty, and you've got an actual number for the y value, well, you can put it into this function. And your x value, you can have an uncertainty in this as well, but it's most common that the x values don't actually have an uncertainty because it's maybe just the number of measurements that you've got and you're plotting them on there, or maybe it's time. And there might be a slight uncertainty in time, maybe if you're using a stopwatch or a clock or something, but it won't be huge. So usually there's only errors in the y-axis. So it's going to add error bars to points on our graphs. And say if we know the error in the x-axis to be 6 units, then we just set x error equal to 6 here. We can also select how often an error bar appears on our graph with the error every variable. So this is a formal parameter name that we're going to change, and we can put whatever we want into it. Here it is down here, error every, where we've set it equal to 20 in this example. It's an integer that represents the number of data points between plotted error bars. It's also a requirement for the format variable. It's spelled FMT, that's short for format, to be set to none for this to work. So here's format, it's set to none, and I'll show you why. So here again, I'm just making some random sine waves with a bit of noise, and I'm plotting an error bar on the point. So every 20 data points here, we've got an error bar. The error bar is orange. The cap size, so I'll show you what the cap size variable does. If I increase that to 60, so you can see it just makes them really big. It looks ridiculous, it's not useful, so keep them. Good value like 6. Cap thickness, change that up to 20. You can see it gets ridiculous, so keep that at a reasonable value as well. and we're putting in our x values, our y values. Here we're putting in the y error. If I increase this to 0, you'll see that the error bars disappear. Here we are. No error at all. Whereas if I put it up to 1, then big error. And if I change the x error as well from 0 to 1, you see we get the same thing. And now also it matches the scale as well. So on the y values, it's gone up by 1. So you see here on the scale, the error bars are matching 1 unit. And then on the x-axis, they're matching 1 unit either way as well. So it's not 1 over the whole bar, it's 1 from the center and up. So that's how you do error bars. That's pretty much everything there is in Python 8. Up next, we're going to be covering further statistical graphs. I'm going to show you how to make the fill-between graph and also the rolling average graph as well. So thanks very much for watching, and I will see you in the next video. Bye.